Hello students, welcome to Sri Jayendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 14 of a unit electrostatic potential and capacitance. So let's begin with today's class. Today we are going to discuss about the energy stored in a charged capacitor. So let's begin. That we are we just want to know that if this is the first positively charged plate, we know that what the capacitor is. It is an two plates or the two parallel plates. What we know is that one of the plate has been given a positive charge, another one has been given a negative charge, and there is certain separation between these two plates. If if some dielectric slab has been inserted to a plate, that capacity would be increases, and if nothing has been inserted between these two plates, that means we consider that air is there as a dielectric medium. So this is a plate where the separation between two plate is the d, and the cross sectional area is a, which is in meter square. So what we understand is from the figure that the process of charging a capacitor is equal to that of transferring charge from one plate to the other plate. That means we are supposed to understand that it is just the transformation of charge from, let's say, from this to this. So we are going to transfer the charge from one plate to another, and that is what we call as the charging of a capacitor. So what we understand is when a potential difference is applied between the two plates, a charge is transferred from one plate to another. That we know from very beginning that we know that Q is equals to C multiplied by delta V. If delta V is 0, if I can say delta V is 0, the transform of a charge would be a 0. So if I applied a potential difference between these two plates, then due to this potential difference, the certain charge is going to flow from one of the plate to another plate. Yes. So let's suppose that potential difference applied between two plates to be considered as a V, and that V could be given as a V is equals to Q by C. Let dq be the extra charge and du be the electrostatic potential energy. Then what I can have is that du, this I know that velocity potential is equals to work done divided by charge. And as I know potential is equals to work done by charge, I know work done or delta work done or delta U, it's in V into Q. I hope this is clear. So this du is equals to V into dq, and that V can be written as Q by C. This is Q by C into dq. Let's take an integration on both the sides. So integration of du from 0 to U, and here it's from charge 0 to charge Q. It is integration of Q dq, because 1 by C is a constant, and keep it aside. So it is U is equals to, this is integration of Q, it's in Q square by 2, and putting up the limits, it's from 0 to Q. This is equals to Q square by 2C. So this is the energy stored, in capacitor, it's in Q square by 2C. Now let's find it out the different forms. Of this energy stored in capacitor. I know that Q is equals to CV. Yes. So this U is equals to 1 by 2. Let's replace this Q with the CV. It's a CV whole square. So this is C square V square divided by C. If it is C square V square divided by C, only one power has been gone and one power would be the left. So this U is equals to half CV square. This is the second relation or second format of the energy stored in capacitor. U is equals to half CV square. Next, again let's replace the Q is equals to CV. I was having the relation that U is equals to half CV square. So let's replace the C with the help of Q by V. If it is there that U is equals to half into Q by V into V square, then it could be U is equals to 1 by 2 QV. This is the third form. U is equals to 1 by 2 Q into V. I hope those things are clear to you. So what we can have, we have a three format. One of them it's in U is equals to half CV square. if if you just summarize this, if you summarize this, then I can have this three format. One of them, it's in U is equals to half CV square. Another is the U is equals to Q square by 2, say it is the second form. And the third, it's the U is equals to QV by 2. This three, all of this are true. It is just the situation which ask me to use the formula accordingly. I hope these things are clear to you. I hope these things are clear to you. Is it that this all formula are equivalent, and they have been used or they have been derived by putting a value of Q is equals to CV and something like that only? Yes. So that is not a question that what should I do and which formula is correct and which formula is the preferred one. There are no any preferred formula would be there. No any preferred formula would be there. You are going to use the formula. You are going to use the formula which helps me to solve the equations or to solve the situation easily. I hope these things are clear to you. Yes. So let's have a look. How could I use this? How could I use this? Suppose what they have asked is that suppose a situation is given that one of the capacitor is there, another is there, and this three are the capacitors. This is of 2 microfarad, this is of 4 microfarad, this is of 6 microfarad, that has been connected with a battery of 10 volt. And they ask that find out energy stored in all three capacitors. So this is the requirement. Find out the energy stored. Find out the energy stored in all three capacitors. So how could I calculate this? What could be the situation? Now, what are the options? First, I need to check out the options. What I am having. It's in first is the U is equals to half CV square. And another is the U is equals to, what I can have is it's the Q square by 2C. And the third option, U is equals to Q into V by 2. So I can use any of this, but which will help me to get it done in a easy manner and in a fast manner. So what I understood is that this all capacitors are connected in parallel combination first, and as they are in parallel combination, their potential difference would be equal. Their potential difference would be equal. So what I can know is that U is equals to half CV square would be the base suitable. So if I want to write, it's a 1 by 2 into 2 microfarad multiplied by 100. This is energy stored in first capacitor. Same way, energy stored in second capacitor, U2 is equals to 1 by 2 multiplied by, I think, 4. Yes, multiplied by 4 into 10 to the power minus of 6 into 100. U3, it is a 1 by 2 multiplied by 6 microfarad multiplied by 100. Yes, if I have been asked the ratio, then U1 is to U2, or something like U1 is to U2 is to U3. What I know is that 1 by 2 would be a gone, C would be a gone, C would be the difference, sorry, my mistake, and V would be the same. So U1 is to U2 is to U3 is there, just the ratio of C1 is to C2 is to C3. It's a 2 is to 4 is to 6, or you can say 1 is to 2 is to 3. So I hope you understand the things, that here these three are connected in series parallel, and when they are connected in parallel, I know that when capacitors are connected in parallel, they are having the same potential difference. And if this people are having same potential difference, I can go, or I should go with the half CV square. Yes, and this will help us. I hope this is clear. Yes. One more question. One more. Yes, but that question would be done by you guys. So be ready with pen and paper. Do it quickly. That this is 10 volt. Again, this is 2 microfarad, 4 microfarad, 6 microfarad. Yes, and let's give them a number that this is first, this is second, this is third. What they ask is that find out ratio of energy stored in capacitors. Which ratios are required? First they required U1 is to U2, and then they required U1 is to U3. So this is what they require, U1 is to U2 and U1 is to U3. This is what they require. How could I do this? What could be done with this? So if you observe this carefully, shall I write the three of the options? Yes, this should be done in back of the mind, that I am having one of the option U is equals to half CV square. Another option it's in Q square by 2C, and the third option is the QV by 2. Yes, this should be done in the back of the mind, that I am having these three equations. Which one would be the most suitable according to this situation? Which one? So if I observe this carefully, then what I can get is that all this are connected in series. Yes, these three of the capacitors are connected in series, and as they are connected in series, the charge flowing through all capacitors will be same. Yes, so Q is the same. If Q is the same, then what I can have is, if Q is the same, what I can have is U1 is to U2. As Q is the same, it's a 1 by C1 is to 1 by C2, and that's it. Yes, things will be done. So it's a C2 is to C1, it's a 4 is to 2, it's a 2 is to 1, and that's it. You did it. Great. Now again U1 is to U3. What can I do? What can I do? U1 is to U3. Its charge would be the same. So this would be on Q3 is to Q1, and Q3 it's a 6 microfarad, Q1 it's a 2 microfarad. This is 3 is to 1. That's it. Did it. Great job. I hope this is clear to you. Is it? Is it? Is it clear to you? Is it? Yes. So I hope you understand this, the approach, and how could I do this, and what should be the correct path, or what would be the path chosen so that I can do it quickly. I hope this is completely understood by you people. Yes? Okay. Now one more thing I want to add here, that suppose this is the capacitor, and initially it is uncharged capacitor. It has been connected with certain battery. This is capacitance C, this is battery V. By some time this capacitor starts charging itself, and it is the situation something like this, that this is, let's say now it is completely charged. Now let's say this is completely charged. So what is energy stored in capacitor? What is energy stored in capacitor? What I can know is this, that it's an U is equals to half CV square, or it's a Q square by 2C, or it's a QV by 2. Now I'm going to ask a different question. Please understood this question very carefully. If this, if someone asks me that find out work done by battery. This is their question, that find out work done by battery. So what I know is that voltage is equals to work done divided by charge. That we know from a very beginning. Yes. So this work done can be written as a Q multiplied by V. If I replace this Q with the help of CV, it's a CV multiplied by V. So this is equals to CV square. Or or let's say work done is equals to Q into, that V could be written as Q by C. It's a Q square by C. So I am having three formula, or three format rather, than these are not the three formulas, these are three formats. It's a first, it's a second, and it's a third. Yes, I can write this work done by battery is Q into V, work done by battery is the CV square, and work done by the battery is Q square into C. But I will recommend that you should always use work done is equals to charge on capacitor multiplied by potential difference across capacitor. This will always lead to you on a correct path. Yes, always use work done is equals to Q multiplied by V. Q is the charge on capacitor and V is the potential difference applied across the capacitor. Now the question arises in your mind may be that, sir, energy stored in capacitor is half CV square or Q square by 2C or QV by 2, or let's say let's pick the QV by 2, but work done by battery is QV. So where the another energy that has been left, because the battery has did a work of QV and the energy stored in capacitor is QV by 2. So whatever the rest of the amount of energy has been wasted in the heat produced. So what is heat produced in the circuit? This is the heat produced in the circuit. Why this it is produced? To charge the capacitor. This heat has been produced in the circuit to charge the capacitor. So always remember this. This is very conceptual. Heat produced should be equal to work done by battery minus of delta U, change in the energy stored in capacitor. Delta U is the change in the energy stored in a capacitor. Now what is work done by battery? Let's say it's a Q square by C. What is the energy, or what is the change in the capacitor energy? It's a Q square by 2C, and the term remain, it's a Q square by 2C. This is 1, this is half, it's in half, you know this. So this is Q square by 2C or half CV square or QV by 2. This is the amount of energy. That has been wasted in the form of heat. I hope you remember this and you understood this. Yes, so this is heat produced in the circuit. So always use this relation, heat produced. Yes, you need to always use this relation, heat produced. What is it? It's a work done by battery. It's a work done by battery minus of delta U of capacitor. Yes, are you done with this? So let's just quickly revise this, that what is energy stored in capacitor? That energy stored in capacitor is half CV square or Q square by 2C or QV by 2. But what is the work done by the battery? find out, if they ask that find out the work done by battery, then work done by battery is work done is equals to Q into V or CV square or Q square by C. So where are the another energy, because energy stored is just the half CV square, but the work done is CV square. So that half of the energy, in this case half of the energy has been wasted in this case in the form of an heat. How could I calculate that what amount of energy has been wasted? Now I can calculate it by having an heat produced, that can be given as work done by battery minus change in the energy of a capacitor. Yes, if I can do this, I can find it out that whatever the amount of heat that has been produced, and that amount of energy has been wasted, or it cannot charge the capacitor up to that much. I hope these things are clear to you. Is it clear? Is it clear? Yes. So let's find it out, something very interesting. Let's discuss energy density. Now first tell me, what do you mean by energy density? Yes, it's an energy divided by volume. When density word is there, when density word is there, it represents divide by volume. Always remember this. Yes. So this here I am going to discuss about the energy density. It's an energy divided by volume. Now, what is energy stored in capacitor? What is energy stored in capacitor? I can write like this. It's in half into C into V square. Now I know that V is equals to E into T, and the C would be is equals to epsilon naught into A divided by T. So if I replace this 2, if I replace this 2 into the U is equals to half CV square, then I can have U is equals to half into C. C is the epsilon naught A by T multiplied by V square. It's an E square multiplied by D square. Here it is the D, here it is a D square. A single power could be a cancel out. So I am remaining with the half into epsilon naught into E square multiplied by A into D. Now this A into D, what is it? It's a volume. Very good. So this is U divided by volume should be is equals to half into epsilon naught into E square. This is the energy density. It's in half into epsilon naught into E square. This is the energy density. Yes, energy density of a capacitor, it's 1 by 2 into epsilon naught into E square. Yes, this is the energy density. I hope these things are clear. Yes, please remember, yes, because these are the certain things that has been asked directly in a form of a formula itself. Yes, so we must remember this, that energy density of a capacitor is 1 by 2 into epsilon naught into E square. Yes, please remember this. We are going to use energy density very soon, but before we go through it, let's find it out some special cases in a form of question itself. So let's begin. That this is capacitor having capacity of C, and this has been connected with battery V. Now they will ask me that if we insert a dielectric slab between plates of a capacitor, while battery is connected find out. Ratios of following. This is what the requirement is. And when they say that they want to insert a dielectric slab, that means they are going to completely insert this. Yes, something like this. So this is the requirement, that if we insert a dielectric slab between plates of a capacitor while battery is still connected, that at that point of time we require the ratio of the following. Yes, battery is connected and capacitor is being charged, and let's say it is a completely charged. Now we need to discuss about the certain ratios. Now which are the ratios? First, C final to the C initial. Yes. Second, Q final to the Q initial. Third, V final to the V initial. Next, fourth, energy final to the energy initial. First, do this thing. When I say initial, that means before dielectric slab inserted, and when I say final, it's an after insertion of slab. So these are the initial and the final. When I say I initial, it's an before dielectric slab inserted, and when I say F, it's an after insertion of slab. So let's begin then. Yes, how could I do this? Is there anything in your mind? What can we do? Yes, what can be done? Tell me. That if you can observe this very carefully in a very detailed manner, you might have an idea that this is connected. My battery is still connected even though a capacitor was there with air, and even now when capacitor is with dielectric slab. So when, if my battery is still connected, if battery is connected every time, then potential difference across the capacitor should remains the same. Yes, that means I can have my first result, that is Vf must be equals to Vi. Now this is very important conclusion, that my potential difference across the capacitor will remain the same. Now according to this I can have a conclusion of different parameters as well. That first, let's say I know that when the capacitor is with air, with air, and now it is with dielectric slab, my capacity increases by k times, so I can write Cf is equals to k times of C. That is for sure. So Cf by Ci would be equals to k, that I know. I have already done with the potential. Vf is equals to Vi. So now it's a turn for the charge. So what I can write for the charge is that Q is equals to C into V. I can write this, Q is equals to C into V. So it is QF, that is equals to final charge, it would be equals to K times of C initial multiplied by V final, and Q initial was the C initial into the V initial, but as I know Vi is equals to Vf, so this is QF is to QI, that is equals to K multiplied by Ci multiplied by V, divide by Ci into V. This 2 has gone, and this is QF by qi, that is again equals to k. This is the ratio of the charges before insertion of dielectric slab and after insertion of dielectric slab. Now I have been left with the energy stored in capacitor. Let's do this. UF is to UI. Now what I should consider is that I have formula of U is equals to, I can use half CV square. Yes, I can use a Q square by 2. Say which one to choose. Which one to choose? As I know that my potential, this is rough work that has been done in your mind, not even on the paper. You cannot use this much amount of time while think. Yes, so you must consider that this is the voltage, and in this case voltage remains the same. So what you can go with is that this is going to cut if I took a ratio. So this only this depends on the C only. So what I can have is it's in half multiplied by capacitance, it's a K times of C initial multiplied by V square, divide by it's in half, it's a half multiplied by C multiplied by V square, and this has been gone, this has been gone, this has been gone. So this energy stored final to the energy stored initial, it's in K, UF by UI, UF by UI, it's in K. Is it clear? Is it? So are you done with this? Can you do this? Are you sure? Are you sure? Yes. So can it be done? Great. So ready to move next, and like to have one more question like this only. Yes. So let's look at this. A question is, these are the special cases, but we are learning this as a form of questions only. Yes, because it will be more logical as well, because it is in the form of a question. And if it was the generally the special cases, that this, if this is the thing, then capacitance will increase and energy will increase, then it would be an certain kind of theory only, and you will get bored with this. Yes. So now the case is that if capacitor has been charged by a battery of potential V, and then battery has been disconnected. Now if dielectric slab has been inserted in capacitor, find out ratios. First, it's in charge final to charge initial. Now you know what is F, what is I. Second, capacitance finals to the capacitance initial. Third, it's in potential final and potential initial. Fourth, it's an energy final is to energy initial. Yes, go through data very carefully, go through this data very carefully, go through it. What they said is that one of the capacitor is there, and that capacitor has been charged by a battery of potential V, and then now battery has been disconnected, and now the situation is that if dielectric slab has been inserted after removal of one battery in capacitor, then find out this ratios. Yes, F is the final, that means the after insertion of dielectric, and I is the initial, it is the before insertion of dielectric. So what could be done and how should we do it? So let's have a rough sketch of it first. This was the capacitor and this has been connected with the battery, and after it has been fully charged, it may be disconnected from the supply. So it might look like this. This is completely charged capacitor, and now our dielectric slab has been inserted to this, something like this. So this is according to them initial situation, this is final situation. So what can we do? Yes, I require the charge, I require the ratios of the charge, ratios of the potential, and ratios of the capacitance, and all this stuff. So what can we do with this question? How can I find it out? Tell me, what can I do and what should be done? What should be done? What I understood is that if in this case battery has been disconnected, if battery has been disconnected, that means charge of the capacitor before and after insertion of dielectric slab should be same. That means Q of initial should be is equals to Q of final. Yes, because now battery is not there, and if no battery is there, if battery has not been connected, there are no one who can change the charge of a battery, that can change the charge of a capacitor. So as battery has been removed, my charge remains the same, and if charge remains the same, I can have the rest of the things. So let's begin. First, it's Qi is to Qf, that I know now, it's a 1 is to 1. Second, capacitance, that I know it's a C final, it is equals to K into C times of initial. C initial is a Ci, so this is K times. Next, what about the voltage? What about the voltage? What I know is that V is equals to Q by C. So if I take a ratio VF is equals to QF divided by CF. VI is equals to Q of I divided by CI. Yes, this CI charge would be gone because they would be the equal, and CF would be equals to K times of CI. So this is equals to 1 by, this is CF is equals to, it's a KCI, it's a 1 by K. This is equals to VF final potential to the initial potential, VF by VI, that would be equals to 1 by K. I hope these things are clear to you. Is it clear? Are you sure? VF by VI, VF by VI, it is equals to 1 by K. And last, it's a fourth, it's a energy stored, it's an energy stored in capacitor. So this is UF by UI. Now again time to rough work within your brain, that which relation should I use. This is Q square by 2C, one of the relation, and another relation, it's in QV by 2, and one more, it's in half CB square. Now look at this. In this case, charge remains the same. So you can go with this. Yes, so this UF should be is equals to QF square divided by 2 into CF multiplied by, this is Q of initial square multiplied by 2 into C of I. This 2 would be a gone, as well as this QF would be gone. So this is CI, this is CF would be equals to K multiplied by CI. So this is UF is to UI, and if I solve this, it's 1 is to K, this is UF is to UI. Yes, so we have learned this two, very logical and very technical as well, two cases. One of the cases when so shall I write this in a form of a summary? Shall I? Yes, let's have a look. That if battery has been connected and dielectric slab is inserted, then potential difference across capacitor should remain the same. This is the first case, that if battery has been connected and dielectric slab is inserted, then potential difference across the capacitor should remain the same. And the second, if battery has been removed and dielectric slab has been inserted, then charge through a capacitor remains the same. Please remember this too. These are the key points that will help me. That if battery has been connected and dielectric slab is inserted, then the potential difference, this will remain the same. And if battery has been removed, if first it was connected, now battery has been removed and the dielectric slab has been inserted, then charge through a capacitor will remain the same. So please remember this. Yes, very logical but very effective. Yes. Now let's look at the next concept, that we are going to study about the force acting on the plates of parallel plate capacitor. We want to find out what is the amount of force that acts, on the parallel plate capacitor. So let's have a look at them. Suppose this is my PPC. It's a parallel plate capacitor. Yes, this plate has been positively charged, this plate has been negatively charged. That means what I can say is this is having a charge of plus Q, this is having a charge of minus Q. The separation between these two plates is T. The T. And the cross-sectional area of each of the plate is A. Now what I need to find out is that I need to find out a force on any one of the plate. Let's suppose I want to find out force on the plate having charge minus Q. That is what my requirement is. Now if you remember, when we are supposed to find out the force, we have a similar approach. What we are going to do is we are going to do this thing only. F is equals to minus of Q multiplied by electric field. Now you must be very careful that who will contribute this electric field, because let's look, when we are used to say this F is equals to Q into E, then I have a very popular keyword that charge will be of mine but electric field will be of someone else. I hope you remember this. Yes, it's a first unit, electric charge and fields. Yes, this charge will be of mine, but electric field will be of someone else. So if I write this, F is equals to minus of Q into E, then electric field will be provided by plus Q charge plate. Electric field will be provided by plus Q charge plate. This is charge plate. Do not consider it as a point charge, and do not write K Q1 Q2 by R square. No, it is not like that. It's a charge plate, so this is equals to minus of Q and electric field due to this charge plate, and it is would be, it's a sigma by 2 epsilon naught. Have you remembered this? Yes, it is the electric field due to charge non-conducting plate. I hope you remember this. Yes, so this is F is equals to minus of Q. F is equals to minus of Q multiplied by sigma. Sigma is equals to Q by A multiplied by 2 epsilon naught. This is equals to minus of Q square divide by 2 into epsilon naught into A. So this is minus of Q square divide by 2 into epsilon naught into A. This minus represents, this is force of attraction. This is force of attraction. So this F is equals to minus of Q square divide by 2 into epsilon naught into A. Yes, yes, got it? Yes. Shall I write some more format of this? F is equals to minus of Q square divide by 2 into epsilon naught A. Yes, I know that sigma is equals to Q by A, so I can replace the Q with the help of sigma into A. So I can also write this as QF is equals to minus of sigma square A square divide by 2 into epsilon naught into A. This A would be a gone, and this is equals to minus of sigma square by 2 epsilon naught multiplied by A. This is force, this is area. So if I write this, it's in force by area. What is it? Force by area. Yes, it is a pressure. This pressure is called as an electrostatic pressure. That is what we call as an electrostatic pressure. That is equals to minus of sigma square divide by 2 epsilon naught. This is equals to minus of sigma square by 2 epsilon naught. Yes. Now shall I replace E is equals to sigma by epsilon naught. So sigma can be replaced by E into epsilon naught. This is equals to minus of E square multiplied by epsilon naught square divided by 2 into epsilon naught. One power has been gone. So this is equals to half, magnitude wise half, into epsilon naught into E square. Yes, this is electrostatic pressure. Magnitude wise, I'm talking about the magnitude wise. This magnitude wise, it is same as the energy density when we calculated at the energy stored in a capacitor. I hope these things are clear to you. Yes, is it clear? Yes. So according to this relation, what I can observe is that force is directly proportional to the square of the charge. Yes, and force is inversely proportional to the 1 by A if charge has been given. Yes, if sigma has been given, please remember this very carefully. If sigma has been given, then force is directly proportional to the square of the sigma. It is even directly proportional to the cross sectional area. Here it is inversely proportional. So you must consider that whether charge has been given or sigma has been given. If sigma has been given, that cross sectional area of a plate is directly proportional to the force acting. But if charge has been given, then cross sectional area is inversely proportional to the force acting. I hope the things are clear to you. Is it clear? Okay, great. Then let's wind it up here. Yes, this is all about the energy stored in capacitor. and we have done as well as the what amount of heat can be produced while charging the capacitor. Then pressure and force acting on the plates of a parallel plate capacitor, and two different very logical cases. Yes, so please revise this, please revise this. This are certain maybe logical, but this has been asked very often, very often. So please revise this, please make a practice a lot. This will save us. Thank you, have a good day, take care.